Okay, so the second speaker for today is Yusheng Luo, and he will talk about renormalization, circle packings, and uniformization. So please.
Thanks for the invitation, and thanks for the introduction. So I want to talk a bit about renormalization, circle packings, and uniformizations. So maybe let me first clarify the definition of a circle packing here. So we study a collection of round disks of the Riemann sphere with the disjoint interior, and then one can associate a combinatorial object called the nerve or the tangency graph for this collection. So basically, this nerve is essentially, you can construct this nerve by associating a vertex for each round disk, and you connect two vertices if the corresponding two disks intersect on this boundary. Right, so in this example of a Polynomial circle packing, there is a vertex for each of these circles, and you introduce a edge connecting two vertices if the two corresponding circles touch. Right, and then in our definition, a circle packing always means that this combinatorial graph is connected. So this graph can be finite or infinite, in which case we have a finite circle packing, or an infinite circle packing, as in this example of a Polynomial circle packing. One should also think about this as if you have an infinite circle packing, this sits on the other end of the spectrum compared to a Sierpinski carpet, where if you have a Sierpinski carpet, the tangency graph of the nerve is totally disconnected. So there is any connected component is a single point. Here, when we say a circle packing, we always mean that the tangency graph is connected. So that's the main player of this talk. And in this talk, I want to discuss some theorems about the renormalizations on these circle packings and some applications in terms of uniformization problems, which is an ongoing joint work with Dimitris. Okay, so is it clear about the definition for the circle packing? Right, so the first natural question that we want to understand about these circle packings is the existence and uniqueness problem. So if we start with a connected plane graph, and can we find a circle packing whose nerve is isomorphic to this graph? And whether it is it unique? Or more generally, what can we say about the space of all circle packings with this graph as a combinatorics? And the last question that we want to address for the first part of this talk is how do we compare the two circle packings with the same combinatorics? Right, so here, a plane graph means that it is a graph that is also embedded in the Riemann sphere. Right, so it's a planar graph together with an embedding. And when we say two plane graphs are isomorphic, we always mean that you have an isomorphism as a graph coming from the homomorphism from the ambient space of the Riemann sphere. Right, so perhaps the first theorem about that addresses all of these questions, or the theorem by Kobe-Andreev-Thurston, the famous finite circle packing theorem. So for a finite graph, I'm sorry. Can you hear me now? Okay, so the battery dies, so I have to use my microphone on my computer. And for a finite graph, then so the Kobe-Andreev-Thurston theorem essentially says that this graph is isomorphic to the nerve of a circle packing if and only if it is simple. Here, simple means no self-loop and no double edge. Or more generally, no multi-edge. So this condition, the simple condition, is easy to see as a necessary condition
for the existence of a circle packing, because if you have a circle packing, the nerve cannot have a self loop, and then you cannot have two circles touching at two different points. But the non-trivial part is really the sufficient part. And Kobe first discovered this, and then was almost forgotten. And Andreev reproved the theorem, and then Thurston uses Andreev's theorems as a reinterpretation of the Kobe's original result. And the second part of this theorem essentially says that the circle packing is unique if and only if this graph is a triangulation. And here, when I say unique, I always mean it's unique up to Mobius maps. So the situation is slightly different if you have a non-triangulation. So let's consider an example where you have a quadrilateral. So this is not a triangulation. This is a plane graph that is not a triangulation. And then it is easy to see that we can draw various different circle packings whose nerve equals to a quadrilateral, and then they're not Mobius homomorphic to each other. Right? And then its moduli space can be constructed by looking at this particular group generated by reflections along these four circles. So this is its index 2 subgroup is some planar group. And in this particular example, this is a quasi-function representation. Quasi-function group, its limit set is going to be a quasi-circle here. And it divides the plane into two regions. And then we have a fundamental domains in the interior and a fundamental domain in the exterior, right? And the moduli space of all circle packings is essentially the quasi-conformal deformation space of this group, this reflection group. And this deformation space, by a classical theorem, can be encoded as the technical space of these ideal polygons. So for each face, you associate an ideal polygon, and the quasi-conformal deformation space is the product of all these technical spaces. So in this case, we have two faces, an ideal quadrilateral inside and an ideal quadrilateral outside. So the technical space is isomorphic to the product space. The deformation space is isomorphic to the product space of the two copies of ideal quadrilateral. So it is isomorphic to R2.
Can I ask a quick question? So how should I think about this space in more intuitive terms? So you essentially put a Beltrami coefficient on each of the fundamental polygons, and then you extend it by reflection and solve the Beltrami equation?
Yes, exactly. So that is exactly, so you have two fundamental regions, and then you can associate a Beltrami differential arbitrarily on these regions, and then you use reflections and uniformize that.
Okay.
All right. Okay, so the infinite, when the graph is infinite, the case is more complicated, and it has been extensively studied in the literature in the 90s and early 2000s for those locally finite triangulations. The first result of this type is perhaps a result by Rodden and Sullivan, which says that if you have the hexagonal circle packing, then it is rigid. A hexagonal circle packing is some circle packings that has this infinite hexagonal pattern. And this has applications in Thurston's discrete Riemann mapping theorem. And later, Schramm and Herr did a lot of work on this topic. They generalized many of these things for the existence and the uniqueness and rigidity for infinite triangulations. And they have a lot of applications, for example, in the Kobe uniformization conjecture. So what I'm going to talk about today is in a slightly different setting. So I'm interested in those graphs with a particular subdivision rule. So let me first give you some examples before telling you the proper definition here. So basically, these graphs with subdivision rules appear naturally in the study of conformal dynamical systems. So they arise naturally because we have some kind of a Markov partition, and the subdivision rule encodes these Markov partitions. And in contrast with this infinite triangulations, these graphs, these infinite graphs are usually not locally finite, and they're not triangulations. So it's a slightly different, it's a different setup compared to these usual settings where you have, which has been studied extensively. Right, so to illustrate the idea of the definition, let me first look at this Apollonian circle packing. Well, if we focus on the Apollonian circle packings bounded by these three circles, then the interior can be constructed inductively by starting with a triangle. Then we subdivide this triangle into three small triangles. And then we obtain, for each triangle, we obtain essentially the same shape as the previous one. So we can continue doing this subdivision. So this is the level 0 is a triangle, level 1 consists of 3 triangles, and level 2 consists of 9 triangles. And so, okay. So, and here are 2 other examples. On top, we start with a quadrilateral, and then we start to subdivide each quadrilateral into 2 quadrilaterals by introducing a vertex in the interior. And this time, the situation is slightly different. In the previous case, because of the symmetry, it doesn't really matter how we are going to identify the small triangle with the bigger one. Here, we have essentially 2 different ways to identify each of these small quadrilaterals with the bigger one. On top, we are going to identify this additional vertex with the upper left. And in this way, the next step is going to introduce a subdivision that connects this additional one to the diagonal, and so on. And once you introduce this identification, then you can iterate this procedure and then obtain an infinite graph. And in the second case, in the second example, we are going to identify this additional vertex with the lower left. And in this way, this subdivision rule will give you this infinite sequence of graphs. Right, so here are some more generalizations of the subdivision rule, but properly speaking, when I say a finite subdivision rule, I mean a collection of polygons with 2 properties. So each of these polygons, Pi, can be subdivided into finitely many small pieces. So that the edge of Pi is not subdivided. Okay, so this is a very important property that we want to use. I will comment more about this in a minute. And the second item in the definition is that we want to have an identification from this small triangle into one of these, small polygons into a one of the polygons in the list. Here, this sigma ij is just some index in this one, some index from 1 to k, and this psi is a homeomorphism. Right, so because the edge is not subdivided, the one skeleton of P1 or Pi can be embedded into the one skeleton of the subdivided graph. Okay, so if we consider, so we are going to set G 0 to be the one skeleton for Pi, or maybe here I'm going to. And more generally, I'm going to set G of n of I to be the one skeleton for the nth subdivision of this this polygon Pi. Right. So because of this identification of the small polygons with the bigger one, we can iterate this procedure. And then we are going to look at this one skeleton, which is going to be a plane graph. And since the edge is not subdivided, we have a natural embedding of G n of I into G m of I if n is less than or equals to n. Right, so this is why we will only want to consider the case where these edges are not subdivided. Right, so we can consider a more general subdivision rules where we allow the slits to be infinite. We allow the subdivided polygons to be infinite. Like these are something like called the Z2 subdivision rules. And we can also look at some interpolations of these finite subdivision rules and so on. But for this talk, let us focus on this particular finite subdivision rule. And in fact, we can simply focus on this particular example, these examples. If we all right, so now let's look at this example and try to understand the corresponding moduli space. All right, so this is a subdivision. This is a sequence of graphs coming from the subdivision rule, and let us denote these graphs by G0, G1, G2, G3, and so on. So each graph is going to be a finite graph. So by the finite circle packing theorem, we can find a circle packing with the corresponding combinatorics, and the corresponding moduli space can be parameterized by the product of the technical space. So for each of these graphs, there is a external face that is not subdivided. And in this case, the external face is a quadrilateral. And then we subdivide each of these interior face into more and more quadrilaterals. So the moduli space of G0 is going to be the product space of two copies of the technical space of the ideal quadrilateral. So it's R2. M of G1 is going to be R3. M of G2 is going to be R5, and so on. Right, so as you can see, the dimension of the moduli spaces increases in this example. Right, so here is our first theorem about the existence and the uniqueness for these graphs with subdivision rule. So if we consider the indirect limit of these subdivision graphs, G of n, so this direct graph is going to be an infinite graph. And let us assume that this is a simple graph. Then the first part is about the existence. There exists a circle packing with this infinite graph as a combinatorics, if and only if the subdivision rule is asymmetrical. So I will tell you the definition of asymmetrical in a moment. Let me just tell you that the first example is asymmetrical, while the second example is not asymmetrical, so it's symmetrical. So the first example is asymmetrical, while the second example is cylindrical. So there exists a circle packing for the first subdivision rule, but there is no such circle packing for the second subdivision. Right. I will tell you the definition of asymmetrical in a moment. And the second part says tells about the rigidity of such circle packings. So assuming that we have a circle packing, so assuming that the subdivision rule is asymmetrical, then the corresponding moduli space is isomorphic to the Tek model space of the external face. So again, let's look at this particular example here. The external face is going to be a quadrilateral. So the moduli space is isomorphic to R in this example. And the third part says essentially about the spherical subdivision graphs. So let me just explain a little bit about what I mean by a spherical subdivision graph. So if you look at this construction of the Apollonian circle packing, one can see that combinatorially, this Apollonian circle packing can be constructed by gluing two copies of triangle together. So you have the interior here, and you have the exterior here. Right. So we say a graph is a spherical subdivision graph if basically you can glue this graph by piecing together different polygons with subdivision rules. So in this example where you have a quadrilateral, one can piece together two quadrilaterals back to back, and in this way we will obtain a spherical subdivision graph. One important feature about the spherical subdivision graph is that there is no face that is not subdivided. There is no external face anymore, so all the faces are subdivided. So in this case, you have a rigid circle packing if the corresponding subdivision rule is asymmetrical. Let me first tell you some consequences of this theorem. The first theorem says, the first corollary says that if you have a geometrically finite linear circle packing, then this circle packing is combinatorial rigid. So in particular, the homeomorphism group of the circle packing is the same as the conformal symmetry group of the circle packing. So the reason it follows from our theorem is because when you have a geometrically finite linear circle packing, so this simply means that the circle packing is also a limit set of a geometrically finite linear group. Then we can construct a certain Markov partition. So this any geometrically finite linear circle packing is a spherical subdivision. The combinatorics, the nerve of this geometrically finite linear circle packing is a spherical subdivision graph. So it follows from our theorem that this the circle packing with spherical subdivision graph is going to be rigid. So this circle packing is also going to be combinatorially rigid. And another corollary is that if you compare two geometrically finite group with the homeomorphic gasket limit set, then they must be commensurable. So one must be finite index of some bigger group, because each one of them is going to be a finite index subgroup of the conformal symmetry group. So they must be commensurable. And here are some examples and non-examples of a linear circle packing. On the left, we have a limit set of a geometrically finite claning group. And you can see that if we pick these 4 circles, then we see the pattern of the subdivision rule from our previous example. So you start with a quadrilateral, and then we subdivided this quadrilateral into 2 by introducing a new vertex in the middle. And we continue doing that for each of these quadrilaterals. And we are going to do the same thing for the exterior. On the right, we have a Julia set of a rational map. And this almost has these 2 sets are almost homomorphic, but they're not. You can see if we look at the corresponding nerve of this limit set, we obtain the same subdivision rule for the interior, and we obtain the same subdivision rule for the exterior. But the gluing is different. For the left, you glue them back to back. For the right figure, you glue them back to back, but together with a 90-degree rotation here. So these 2 sets are not homomorphic. They are locally homomorphic. And in fact, they will play a very important role in our application. So these 2 sets are quasiconformally, locally quasiconformally homomorphic, but not globally quasiconformally homomorphic. Okay, so let me tell you the definition of the asymmetrical asymmetricity, and this is motivated by this. If we consider the group generated by reflections and then the quotient 3 manifold, this 3 manifold is being asymmetrical or not. So the definition of asymmetrical is the following. So if we consider any pair of non-adjacent vertices in the level 0 graph, we say it is asymmetrical if there is a path in this limiting graph that separates V and W. Okay, so to illustrate this this definition in our example here, if we look at these 2 examples, there are 2 different non-adjacent pairs of the level 0 graph. We can pick these 2, or we can pick these 2. Okay, so if we pick V and W in this way, then if we look at the level 2 graph, there is a path that separates V and W. So this means that this graph, and similarly, if we pick the other pair of diagonal vertices, we can already find a path that separates the 2 for level 1 graph. So this means that the first example is asymmetrical. On the other hand, for the second example, if we pick V and W as this pair of non-adjacent vertices, there is no way you can find a path that separates V and W. So this is an example of a cylindrical subdivision rule. Okay, so now let me tell you about the strategy of the proof. And in fact, we prove a slightly stronger notion of convergence here. So, okay, so the idea is the following. So as I mentioned, we have a natural embedding of these level 0 graph into level 1 graph, into level 2 graph, and so on. Okay, so this natural embedding induces the pullback map on the moduli spaces. So in other words, if we start with a circle packing whose nerve is isomorphic to G2, then I can forget about these additional vertices. And then we can look at the subcircle packing whose nerve is isomorphic to G1. And we will call such maps tau the skinny map, because they are related to the skinny map, the Thurston skinny map for 3 manifolds. Okay, and then the proof consists of 2 steps. The first step is to show that essentially the skinny map has bounded image. So in other words, there exists a universal number n such that if we look at tau to the n of the moduli space G of n with n greater or equals to m, the diameter of this with respect to the usual technical metric is bounded. Okay, so this, if you iterate long enough, this the image of this moduli space is going to be bounded, right? And the second part follows from the fact that this tau is the restriction of some holomorphic map. But this, although these moduli spaces are not complex manifold, but they are real slices of some complex manifold. And this tau is the restriction on these real slices of some holomorphic map, and then technical metric is the Kobe-Andreev metric. So you have this contraction with respect to the technical metric. And because we have this bounded image, we prove that this contraction is uniform. So there exists some delta, so that this derivative, the nth iterate, or the derivative of the nth iterate of this skinny map is going to be delta to the n, basically. All right, so this allows us to prove a much stronger result than the existence and the rigidity theorem. So in particular, we prove the following exponential convergence theorem. So if we have P, let's say n plus k, or k plus n, and q k plus n, there are circle packings whose nerve equal to the k plus nth graph, level k plus nth graph of the subdivision rule. And let us assume that they have the same external class. So this moduli space is the product of the technical space, and then in particular we have one factor coming from the technical space of the external face. And we assume they have the same external parameter here. Then if we look at the technical distance between PK and QK, this is going to be all of delta n. Here, this PK is the nth iterate of the skinny map on this k plus n, and the QK equals to the nth iterate of the skinny map of qk plus n. Okay, so here is an illustration, which I think it's better to look at some movies here. Okay, so let me try to explain this movie a little bit. Okay, so here we have a sequence of finite circle packings. And you can see as we add more and more details to this finite circle packing, the outside four circles kind of wiggled only a little bit. So they almost stabilize this exponentially fast. So as we add more details to this circle packing, the lower level circle stabilizes exponentially fast. And that's the content of our exponential convergence theorem for finite approximation. Okay, so once we have this exponential convergence, the existence and uniqueness part follows almost immediately. Okay, so I'm going to skip that. And let me also tell you a little bit about another version of the kind of the finite approximation. So instead of zooming out, when we start with a very finite circle packing with a lot of details, and then we kind of like look at more and more shallow levels of the circle packing, we can also do the other operation, zooming in. So we start with the infinite circle packing, and we pick a point that is in the that is somewhere like in the limit set of this circle packing. And then we can start zooming in by forgetting about the lower level circle packings here. So this is an example where we start with a quadrilateral, and then we can look at the corresponding level 1 curve, level 1 graph, and then we start to zoom in. And we also prove a version of the geometric inflexibility for these renormalizations. So although these circle packings are not rigid, but they're geometrically inflexible. So what do I mean by that? So if we start with the two circle packings, P and Q, whose nerve equals to this infinite graph. So you have the infinite circle packings. And if we start zooming in at a point, so let me assume Px equals to Q of y is homomorphic. Then we can start look at the nth iterate of this renormalization. Then this distance between the technical distance between the nth iterate of this renormalization and compared to the nth iterate of this renormalization for Q also converges exponentially. So this means that if you have any homomorphism or any quasi-conformal homomorphism between these two circle packings, this quasi-conformal homomorphism is almost conformal at deep points, at these deeper levels of the circle packings. And this is what we mean by this geometric inflexibility here. Okay. Any questions about this? Now I want to talk some applications about this these exponential convergence theorems for the uniformization problem. So the underlying question is, can we when we start with a gasket, a topological, like something that mimics like that looks like a circle packing, can we simultaneously map the boundary of a gasket to round circles? So in the setup of Ntalampekos carpet, there is a sufficient conditions for quasi-conformal uniformizations by Marie Bonk. And in the dynamical setting, there is a theorem by Kurt McMullen, which says that if you have a gasket limit set of a geometrically finite Kleinian group, then you can always quasi-conformally homeomorphic map it quasi-conformally homeomorphic to a round circle packing. And then there has been many other results about these quasi-conformal uniformizations of the Julia set, Ntalampekos carpet Julia set, and so on. So I want to study these questions in the dynamical setting. So the questions that I want to understand is, if we have a Julia set that is a gasket, well, can we uniformize a gasket Julia set? All right, so there are some local obstructions for the uniformization. So for example, the first type of the obstruction comes from the two circles. So in general, if you have two Jordan domains, the two Jordan domains might touch, but this touching point might have some angle in between them. And if you have an angle, then this is a quasi-conformal obstruction. And this happens if you have a point that is a repelling point. And this is a QC obstruction. Okay, so there is another type of local obstruction. So another picture might look something like this. I'm going to draw a cartoon picture. Right, so this happens if this point is going to be a parabolic point of multiplicity . Two. Okay, so in this case, this is not only a QC obstruction, but it is also a David obstruction. So you cannot map a cusp of a parabolic neighborhood of a parabolic periodic points of multiplicity 2 by a David homeomorphism to a round disk. So we couldn't find a precise reference for that, so we have to reprove that statement. Okay, so basically, so what we prove is that these are the only two types of obstructions. And here is a result that uses our ideas about these exponential convergence and this geometric inflexibilities for these infinite circle packings of subdivision rules. We were able to apply our results to this uniformization problem. So the first is the characterizations of the quasi-conformal uniformizations of the Julia set. So the setup is the following. We start with a rational map without Julia critical points, and whose Julia set is a gasket. So unfortunately, I didn't define what I mean by a gasket, but for now, you can think about a gasket as something being homomorphic to a circle packing. But we are the condition is actually slightly weaker than that. Then we have the following characterization. So there we can simultaneously map all the boundary of these two components to a round circle by a quasi-conformal map, if and only if this gasket is a fat gasket, and if and only if every contact point is eventually mapped to a parabolic periodic point with multiplicity 3. So you cannot have this contact point is eventually mapped to something that is periodic. That's easy to see. And these periodic points can either be repelling or parabolic with multiplicity 2. So if you have the first situation, then you have an angle. If you have the second situation, then you have a cusp. So if you do not have these two cases, then you can actually quasi-conformally uniformize this Julia set. And the second part is about David uniformization. Again, we are working with the same setup. We start with a rational map with no critical points on the Julia set, and whose Julia set is a gasket. Then we prove the following are equivalent. So we can map the boundary of each two component simultaneously to a round circle by a David homomorphism if and only if each component is a quasi-disk. So that is, we rule out these cusps. We do not have any cusps on the boundary of the two component. And if and only if every contact point is eventually mapped to some repelling periodic point or parabolic periodic points with multiplicity 3. So you cannot map it to a parabolic periodic point with multiplicity 2. So that's the only obstruction here. Okay, so as a consequence of this uniformization theorem, so we can go back to this picture of a geometrically finite Kleinian circle packing and a gasket Julia set. So what we prove here applies in this setting. So on the right, we have a fat gasket. So in fact, every contact point is eventually mapped to this particular point. And this particular point is parabolic with multiplicity 3. Okay, so this our theorem applies to this gasket Julia set. So we can uniformize this by a quasi-conformal map to an actual round circle packing. And if we look at this region bounded by these 4 circles, and the corresponding 4 circles here, you see the exterior, they look the same, and in fact, they are indeed homomorphic. So they're actually quasi-conformally homomorphic by our theorem. And if you look at the interior bounded by these 4 circles, they almost look the same. If we rotate by 90 degrees, then they're exactly the same. Okay, so this, and then in fact, when we rotate by 90 degrees, they are quasi-conformally homomorphic as well. So what we can construct here is a very interesting example where you have a Kleinian circle packing and a gasket Julia set. They are locally quasi-conformally homomorphic, but not globally homomorphic. So in some sense, this was motivated by like a conjecture, which asks whether we can find any non-trivial examples of a Kleinian limit set for a Kleinian group and a Julia set for some rational map that are quasi-conformally homomorphic. And I think the conjecture is that there are no such non-trivial examples. But this particular example at least shows that the local version of this conjecture is false. So locally, they can be quasi-conformally homeomorphic. And this is a very non-trivial example. But we still believe that there are no global quasi-conformal homeomorphism. And in fact, we work with this gasket Julia set and then these geometry finite plane and circle packings. And then we prove in various different settings that they are not globally quasi-conformally homeomorphic. But we expect the answer is no for these gasket Julia set and this plane and circle packings, but we still don't know the answer. Right. So in particular, our theorem applies for the setup of a Polonian circle packing, and then as a corollary of our result, we prove that there's no Julia cell that is quasi-conformally homomorphic to the Polonian circle packing. But the question whether we can find any, we can prove that for any Polonian circle packing remains open. Right. Okay. So thank you so much.
Yeah, thanks a lot. Let's thank the speaker. And let me open the discussion, comments or questions.
Hi, so I have a question about this acylindrical condition. I forgot a little bit the definition, but how typical is it? I mean, you have a rule for subdivision, and
right.
How often is it non-acylindrical?
Yeah, most of the cases they are going to be cylindrical, acylindrical.
Oh,
like, I mean, when you have a cylindrical example, you will typically see something like this. So you will see like more and more
I see.
kind of finite connections between two edges.
Mm-hmm.
Oh, sorry, finite connection, finite, you will see more and more paths of finite length, of a bounded length, uniformly bounded length that connects two vertices.
I see.
And then it is easy to see that this is not possible for the realizations of two circle packings. So in this example here, what we're going to see is that you have two circles here that are not adjacent, that do not touch because there's no edge between these two vertices. But you will have more and more circles touching both of them. Right? And then this would mean that this modulus between of this annulus is shrinking to 0. So this is where you have the bounded image theorem actually fails. So if you have a cylindrical subdivision rule, then the skinny map is no longer going to have bounded image, unlike in the acylindrical setting.
And I have the same question, but for your second theorem, where you have some equivalent conditions, and one condition is that you have fat gasket. So for example, how often does it happen that you...
Right, that's a good question. So it is not, I would say, okay, so for example, there are infinitely many such examples in the quadratic case, infinite non-homeomorphic examples in the quadratic case. So for quadratic rational map, there are infinitely many non-homeomorphic fat gasket. But still, like it is not very easy to find them.
Mm-hmm.
So if you have a typical gasket, the chances are it is not going to be homomorphic to a fat gasket.
Thanks.
Well, so I have a question. I mean, you alluded to this in your talk. So what is actually a good topological definition of a gasket? How do you...
Right, yeah. So this is the definition that we're using. So a topological gasket is going to be some some closed set whose complementary regions are Jordan domains. And two Jordan domains, they are either disjoint, their closures are either disjoint or they touch at exactly one point. And there are no three Jordan domains touch at one point. And we also impose this condition that the contact graph, once we have these conditions, we can construct the contact graph. We will also impose this condition that the contact graph is going to be connected.
Yeah,
So not every gasket is going to be homomorphic to a circle packing because you still need some conditions, geometric conditions to guarantee that you have a homomorphism. But like for gasket arising in dynamical systems, for Julia set, then this is we actually can prove that they are always homomorphic to a circle packing.
Okay, thanks. Yeah, that makes a lot of sense. Other comments or questions?
Can I ask a question?
Yeah.
So in your talk, there was some part you mentioned about the renormalizations, and you had like exponential convergence of renormalizations.
Right.
So in a different renormalization theory, people work very hard to obtain some kind of a priori bound to start with. Then from there, you conclude some contraction or exponential convergence and so on. So do you need to have some like a priori estimate in your settings?
So I think the analog of the a priori bound comes from this bounded image theorem. So we know that the image under certain iterations is bounded, then like we can automatically promote that to uniform contraction. So, and then the proof for this bounded image theorem is actually not too hard. You can apply the theorem of Thurston directly, but we can also prove that by hand because we're working with circle packings here.
So can you show the bounded image theorem? The slide?
Yes.
Yeah, so do you have some, are you assuming some uniformity about the subdivision rules and so on to obtain the bounded image?
Yes, that's a great question. So I think because we are only working with one fixed subdivision rule, so automatically it is kind of it is automatically uniform in the sense that like once we pass, okay, so if we work with this subdivision rule, and then if we pass to the second iterate, you can see we can find a path that separates any non-adjacent vertices. So, and then the same thing applies here. Like if we work with G1, and then if we look at G3, then any two vertices, non-adjacent vertices in G1 is going to be separated by some path in G3. So this is the uniformity that would allow us to prove the bounded image there, basically. So the uniformity comes from the definition of the subdivision rule. And in some cases, there are situations where the subdivision rule is not uniform, like we can study these more general like interpolations of these subdivision rules. Or maybe another example would be like one can study, I mean, this might be a very long answer to your question, but there are situations where we do not have this uniformity. And this is some kind of ongoing project, and I think in many cases we can still prove this this kind of like estimate, and then the proof is going to be much harder.
I see. So, for example, for Feigenbaum, like unimodal mapping, renormalization, there are questions about the bounded type or unbounded type. And what you did is more like a bounded type.
Bounded type, exactly. So this is an analog of a bounded type renormalization. Yes. So we fix the combinatorics for all things, but then you can obviously change the combinatorics as you vary your subdivision rule, and then in which case the theory becomes harder, and you want to consider these cancellations and things like that.
Okay. Thank you very much.
Thank you.